Hi, I'm Kyle. I'm a software engineer at a company called Development Seed, and I work on some open source projects, one of which is called Lonboard, which connects Python to Deck.gl in a really efficient way using this technology called Geoarrow. Also, I apologize if I fall asleep during the talk. I flew in this morning and I'm tired. So we'll start diving into Lonboard, especially why it makes users' lives easier. Go into the GeoArrow ecosystem, dive under the hood a little bit in Lonboard, and talk about future work. So the goal with Lonboard is really, can we get simpler, faster rendering of large analytical vector data sets from Python? And especially for users who don't know anything other than Python, who don't want to make their own JavaScript libraries, who just want to visualize their data, explore it, and then maybe change their analysis in some way. So first, why not existing Python libraries? Well, there's an existing library called IPyLeaflet, which binds to the Leaflet JavaScript map rendering library. And it can render up to 300,000 points. It crashed my browser trying to render more than 300,000 points. And it still took almost a minute to render that, even without any network transfer, where Python was on the same machine. And so PyDeck binds to Deck.gl and is more capable, but it still has a lot of overhead because it's using GeoJSON for data transport between Python over the network into the browser, and then Deck.gl has to build buffers back from the GeoJSON objects. And so here's Lonboard. It's almost Axis. And actually it keeps going because Lonboard is not just faster, but it's able to be more capable because it can handle this binary data transport from Python into Deck.gl. And so here, this is rendering 3 million points from GeoPandas in Python into this interactive Deck.gl context in 2.5 seconds. So here, every single point is given its own radius and its own color. And those are computed on the Python side, still in this 2.5 seconds. All of the data is serialized, sent to the browser, unpacked, and copied to the GPU. Here, this is Python is running on the same machine as the browser in this case. Sometimes Python will be running in a remote cloud environment, and then you have some network transfer. So this doesn't have any network transfer in this 2.5 seconds. That's like this memory copy just into the browser, but it's still fast. And actually, this is really GPU bound, not CPU bound. And so on this recent Mac, I was able to render 15 million points, which was laggy when I was rendering all 15 million points. This is like the same data set that I just kind of duplicated a couple times. And so pretty laggy, not fun to work with this on the CPU, but it does work. You could say that's a testament to how good Deck.gl is and how efficient it is with GPU compute. I know people who have used Lonboard with larger GPUs and have rendered like 50 million points. And so it's really only depends on the strength of your local GPU on the computer that's rendering the data. And so here, I maybe usually give this talk to a slightly less technical audience, but here you probably already know that you have to get the data into the browser, manage it, and render it to screen. And so in a case like IPyLeaflet, it's super slow because we have to load the data in a GeoJSON string, which is a really, really big string, a big object to send to the browser. It takes a while to parse that data. And then once it's parsed, you have JavaScript objects that you can't share from the main thread to a worker. You also can't copy directly into binary context like WebAssembly. You can't copy it into the GPU directly. And so you have to, Leaflet in this case would iterate over all of the input features and render to canvas. But using binary data and Deck.gl is a lot faster. And so GeoParquet is an efficient serialization format for binary data that's columnar and has really efficient compression. So it has, it's like maybe a tenth of the size of the relevant GeoJSON data. And a GeoArrow is this binary representation of these tables in memory that is, there's no, because it's binary, you can transfer it between the main thread and a worker thread. There's no garbage collector overhead, and you can interface with WebAssembly pretty easily. And as long as those binary buffers are in the same attribute layout the Deck.gl expects, you can copy mostly directly to the GPU and get Deck.gl's vectorized draw calls. And so Lonboard's really powerful because it has this end-to-end binary data pipeline where it doesn't use JSON, it doesn't use JavaScript objects in any portion of the process here. And so any widget is a Python JavaScript library that manages the Jupyter data transfer for us. It kind of wraps the Jupyter WebSocket that the low-level Jupyter primitives provide. So we take some input format like GeoPandas, DuckDB. We try and integrate with whatever data sources, data libraries that users already working with. Under the hood, convert that into this GeoArrow format, and then copy that to GeoParquet, because we don't know from the Python library whether the user is on the same machine as the browser that is rendering the data or not. And so it's better for everybody to spend a little bit more time to save to GeoParquet when it makes it like 10 times smaller or much smaller to download when it is the case of a remote connection. And then we can unpack that efficiently in WebAssembly and copy to the GPU. And so at a high level, we try and ensure that it's easy to use for users who don't know what GeoArrow is, what Deck.gl is even. Integrate with some of those existing libraries. So we integrate with DuckDB. You can pass in a SQL query and a connection. This will manage the integration with DuckDB, how to efficiently get that data out of DuckDB, copy it into these GeoArrow geometries, and do the rest of the process. A couple other features of Lonboard, it even has a CLI. If you have some data on disk locally, it'll use GDAL's new arrow support to really quickly load that data into memory and pass that into Deck.gl into a static HTML file. Lonboard also has HTML export, so it will include the full data in the HTML file as base64, but it means that you can look at, create a map, export it to HTML, send that to somebody else, and they'll be able to see the exact same map with the same performance. Because Lonboard is built on Jupyter, it allows us to do things like separating the main data and the attribute data in different contexts. So if you say want to change the color map, as we're doing here, the only data that needs to be sent from Python to JavaScript again is the updated color buffer, not the original data, not the radius data, not any other data. The only thing that needs to be sent is this new buffer. And that can happen pretty quickly. And so we can make it more interactive for users. We also have some wrappers around other extensions. Here, this is GPU data filtering of air quality data in Houston. And this is fast because it's only sending the updated range values to Deck.gl. This wraps the Deck.gl data filter extension and is pretty efficient. Some more examples on the documentation website. This is with Overture data. We don't have a wrapper around the entire Deck.gl API yet, but I've been trying to mimic some of the existing Deck.gl examples. So here, this is the arc layer and the brushing extension. We try to support, we support so far the collision filter extension, the brushing extension, and the data filter extension. There's also some Python dashboard applications that try and enable you to build a website on top of Python and Jupyter widgets. And so there's at least some proof of concepts of this working, of creating This is like Lonboard working inside a Python-based app in the browser. I don't know anybody like doing that in production, but at least in theory could work. The deck is a part of a skateboard you ride on, fast geospatial skateboard, a longboard. Yeah, so that's why we were trying to search for a funny name, and then I like that name, and then people never get why it's called Lonboard, so I figured that's a good thing to mention. So let's step back and talk about GeoArrow. So I work at Development Seed. We do geospatial consulting for especially climate and international development. We get to choose partners that are aligned on open source. So actually, Lonboard was heavily funded so far with a standing contract we have with NASA and OpenAQ. That air quality demo you saw in Houston was some OpenAQ data that they wanted to enable better visualization of air quality data from Python. And so I get to do a lot of work in open source to try and make the geospatial data science ecosystem better, especially from Python. But of course, visualization is a big part of geospatial workflows. And so GeoArrow is a project that I've been working on for a while that builds on top of the Apache Arrow specification. So it's a language independent protocol for data layout, where if you go to like the Apache Arrow webpage, you'll see something like this, but for data frame libraries, where Apache Arrow was created so that you could move data between R and databases and Python and pandas much easier than you used to be able to. And similarly, in geospatial data, we have all of these different applications, databases, Python libraries, R libraries, QGIS, and stuff like Deck.gl that we want to be able to interface more efficiently. And so with GeoArrow, we have a single memory layout that we don't have to do a ton of copy and convert between different formats. We only have to do one, which also makes it easier for every library to interface with every other library because you only need one input and output memory format. And then this bar graph is an example of GDAL implemented support for GeoArrow. And this was really valuable for GDAL because GDAL has an internal C representation, but then it wants to exchange data with higher level languages like R or Python. And so historically, the way it did that was by reading a shapefile, say, in C into some binary representation, but then serializing into GeoJSON to copy into Python, which would then parse back into the C. And so this made it 30 times faster when it adopted this GeoArrow layout and API to get data from a GDAL supported driver into a Python. And so I'm really excited about GeoArrow to make it this lingua franca of geospatial data. And so I've talked to some people about stuff like well-known binary, and how I look at GeoArrow is slightly different because well-known binary is a serialization format that you have to unpack into something. And then I argue that GeoArrow is the commonality that everyone should be storing their output in memory. And so I'm trying to build an ecosystem of tools, not just the visualization, but also compute tools that work together really efficiently. This also means that I care about the exact GeoArrow memory layout. And so my personal priorities are more around this than stuff like the existing Deck.gl binary features layout, because there's nice behavior when everybody uses the exact same memory layout with zero copy data exchange. And then, so I'm excited about Lonboard as data visualization, but also as a way to get more and more people to use this ecosystem, even when they don't know what's going on under the hood, because it'll work even better with future tools that will be built around GeoArrow. So an example of this ecosystem is there's this project called Overture Maps that is a consortium of a few different large companies that is building on top of OpenStreetMap. And they have this Explorer website, explore.overturemaps.org. And this reads from their 2.4 billion row buildings data set directly into the browser from their GeoParquet data set. And so here, this has a lot of potential for being able to render large data sets, portions of large data sets on the fly. So here, right now, their visualization is actually not Geopark or Deck.gl, but this shows that we can do this remote. The next version will be faster because of some technical issues that you can talk about directly. At this point, let's jump into a demo. Is this too small? Maybe go to there. So Python is usually a server running thing, but there's also this awesome project called Pyodide that runs Python actually in your browser in WebAssembly. And so in this example, we are literally, we aren't connected to any server. This is running Python in WebAssembly in the browser. Let's run through some of these cells, since some of those take a second to load. So this is using GeoArrow Rust compiled to Python in a way that will work in WebAssembly. This is loading GeoParquet data, parsing this using a Rust GeoParquet reader, or this is actually not even fully GeoParquet. This is parsing well-known text into geometries, accessing the centroid, and then this is the same demo as I tend to reach for by default, which renders download speed, internet download speed from this UCLA. If you ever go to speedtest.net, your data is aggregated and put into the AWS open data. And so here we can, on the fly, use the data filter extension to visualize these 3 million points based on these download and upload latency statistics. And so it's awesome that all of this exists in WebAssembly, but you saw that still took a little while to render the map. And so some of this future work that I'm excited about, because we're using the exact same memory layout, is that we can view the data directly inside Python's WebAssembly memory into JavaScript and then copy to the GPU without having to do a lot of serialization like we do right now, where this uses the same parquet under the hood.
So what is it that makes this slow? Like what is slowing this down mainly?
Well, like this took maybe 5 seconds to render the map. And partially that's because it's using the exact same behavior as it does outside the browser, which means it serializes to Parquet, copies to the browser, which in this case means copies outside of WebAssembly to a different WebAssembly context, parses the Parquet back in Arrow, and then copies that to the GPU. But that in the future, I got a prototype working of viewing an arrow array that was sitting in Python memory in JavaScript without copying it. And so we could pass that table object, that arrow table, which is actually using UN8 arrays that are views on slices of WebAssembly memory that could be passed into Deck.gl. Now, the tricky thing there is you have to make sure that the Python object is like still valid. So if you delete the Python object, then you could get some messy stuff. But at least in principle, that would be pretty cool, especially in this memory constrained environment.
So in that flowchart you had earlier, you had GeoParquet as one of the pieces in that flowchart. You're saying we remove that, which would help.
Yeah, I'm saying we can remove that in specific situations, but kind of using this as an example to show why I'm excited about GeoArrow and all pieces of the puzzle, because it opens up some cool zero copy use cases that are like Python in the browser and then visualizing your data like immediately. It would just be really cool.
For example, in the case of Overture that you were mentioning, since the data is encoded in GeoParquet, but it's actually well-known binary, I mean, you wouldn't actually benefit from this, right? You still have to call out parse well-known binary into GeoArrow and then.
Yeah, I mean, I think for the case of the Geo or the Overture data, like that's this Python use case is still, you have data that you're exploring in Python that in this case happened to be in the browser, but really focused on these iterative exploratory data cases. Yeah, let me maybe come back to that if we have a question. Yeah. So now let's go into Lonboard's internal architecture a little bit. I have a page in the documentation that goes into a somewhat deep dive of Lonboard and how it's laid out and its goals. And so here, this really the target user of Lonboard is Python user who doesn't know or wants to know JavaScript, wants fast exploratory data analysis, already has their data in Python, and has a reasonably fast internet connection. So Lonboard will take the data as arrow, serialize it to Parquet, and then uses a library called Parquet WASM that is the Rust Parquet implementation compiled WebAssembly to parse that into arrow. Here, this is a slide from Xiaoji, the Deck.gl technical deep dive that shows the columnar buffer layout. And so one of the key things about Lonboard is that we don't serialize functions to JavaScript, where PyDeck previously would have this syntax that tries to describe which pieces of the JavaScript objects that were decoded from JSON should be passed into which accessors. But because we do all of this pre-packing on the Python side, we have these binary arrays that we can pass directly into Deck.gl's binary attribute support. This also means that it's hard to work with tiled data that doesn't go through Python. And so stuff like the MVT layer isn't currently supported because we would have to have some styling language to apply the styling to these MVT tiles that we didn't create as arrow objects in Python. There is also this intermediate library called Deck.gl layers that's also been forked into the community repo as the arrow layers module. So GeoArrow generally has arrays that are of a single type. So you might have a point array that has X, Y, X, Y, X, Y of points in a single geometry of the entire table. We map an arrow table of points into a list of scatterplot layers, and similarly an arrow table of polygons into a list of solid polygon or polygon layers. We also have to manage the row index so that when we render multi-points, we have multiple points per logical geometry. So when you do picking, we want to get the index that was rendered and then map that back to the logical index in the table so that you can get the correct attributes for that row. Let's skip some of that for time. So this is a wrapper library that is, it's relatively stable. And so I've been focused more on the Python implementation or Python features than JavaScript feature recently. So this is really focused on not copying or modifying the arrow data to have it as fast as possible for arrow. This runs ear cut on up to like 4 or 6 worker threads, and it uses arrow to post message that those arrays from the main thread to each worker. And then future working on a new Lonboard release, upgrading to Deck.gl v9, working in WebAssembly. Removed a lot of required dependencies, but it's slimmer and easier to have in your environment. Support for categorical data filtering. Ideally, we'll get bounding box data selection in as well, where we have this bounding box picker on the front end, but need to manage the actual picking in Deck.gl. I don't do enough JavaScript anymore. We hit this bug that I still haven't figured out how to make a minimal reproducible example for. So the heat map layer right now doesn't actually work in the unreleased version of Lonboard. One thing that we do with Lonboard as well is that if a user passes in a geodata frame, every single row of that geodata frame is sent to the browser, and all of it is rendered by Deck.gl. It would be cool if we could handle, say, hundreds of megabytes of data in Python and then do dynamic tiling on the fly in Python, that then we would still know how to style. And so I've been porting some libraries into Rust with Python bindings that each are ports of Mapbox libraries to do such as point clustering and efficient spatial indexes, so that we can only transfer essentially tiled data into the browser. I have a branch that has at least a working prototype of the trips layer in Python. This is using Python to kind of drive the animation, and so it's a little bit slower than a pure JavaScript app, but it still is more capable than any Python library so far, and so I'd like to get that in as well. We have a prototype of raster data rendering. This is still rendering PNGs, but it uses raster.io on the Python side to generate the tiles. But because of threading async issues, I'm not sure that this would work well when the raster data is actually remote instead of on your computer. So not sure whether to merge that or whatever. Also trying to work on better extensions and connections to other libraries in the ecosystem. So this is on the top is a viewer called Quack that is a data profiler and explorer that's built on top of DuckDB. And so you can change your selections. This isn't a particularly interesting data set, but you can select data and then connect that to Deck.gl with a Boolean categorical filter to decide which rows based on this DuckDB SQL query should actually be rendered, that we are also selecting that data view in the top and matching that to the map on the bottom. Ideally, some Deck.gl Geoarrow or arrow layers updates handle separated coordinates. The Geoarrow can either be interleaved, x, y, x, y, x, y, or x, 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 x in one column and y in the other. Handle geometry collection and mixed arrays, which is equivalent to the GeoJSON layer, where it would forward to a sublayer based on the correct type of the array under the hood. I have some bugs, kind of long-standing bugs that haven't been fixed, especially with auto highlight, where it because of that distinction between the rendered index and the logical index, when you highlight over a multi-polygon, sometimes it'll show up multiple. And so here it's highlighting like 12 boxes, even though you're only highlighting actually one. And yeah, so the reason really why I started with Lonboard and Python is because it's easier to control both the Python producer of the data and the consumer in JavaScript. But all of this is accessible from JavaScript as well. And so the easier it is to build tooling that brings in data as Geoarrow, the easier it is to build applications with the same performance as you can get with Lonboard and Python, and ideally as good performance as possible with Deck.gl's binary API. And so I'm personally focused on leveraging the same Rust code that I'm working on under the hood so that I can build both Python and JavaScript APIs. This kind of overlaps with some loaders goals. And so I'm supportive of the pure JavaScript loaders as well. And I think that if we all kind of have better arrow support, then hopefully that'll be good for the ecosystem as a whole. And it's good to have the choice of whether you want the pure JavaScript or the WebAssembly version of reading some file. But yeah, thank you.
How does this relate to the new MapLibre tile format, though, that people started working on?
I mean, I'm not an expert on the format, but I don't think it really relates. I know they had some idea of columnar data, right, when they were making the spec, but it's not Geoarrow. I think Geoarrow is focused on, like, you're not simplifying the data, whereas vector tiles, usually, I'm not with MapLibre tiles, but usually simplify the data to make it easier to visualize at different scales. So it seems like they probably have two different use cases.
So the Geoarrow is more of a kind of, here's all the data and just.
It's like GeoJSON. It could represent the original data. It could represent a simplified version, whereas vector tiles are really focused only on the visualization.
in a way, kind of like brings a little bit the discussions that we think on the GL too, which is you have to pass more or less for performance on large data sets. You're trying to squeeze every performance that you can by having access to the entire data set, plus the other kind of like a strategy, which is kind of like the tiling system. You simplify and then you program loading. So there's some preloading around it as well that we've been using for a long time, right? So the question is like, will GeoArrow in a kind of like tile architecture really be a very big benefit, considering that normally, I mean, like a tile is never more than 500 kilobytes of, like geometry in a way. So that's where it gets a little bit complicated, right? Because probably, like Lonboard is really fast of anything up to, like you said, like 60 million all client side, considering that you don't have to transfer the whole thing or something like that. But then after that, you hit that limit. And then you have to start thinking about like, like buffering the data. I mean, like streaming the data in some sort.
I mean, one of the things I want to prototype is essentially a GeoArrow dynamic tiler in Rust Python that emits tiles of arrow tiles to Deck.gl to render.
Right.
That would still assume that you have the data, at least for now, assume that you have 100 megabytes or 200 megabytes of data, but in Python already. I think that Arrow has potential to still be really efficient for both server to create and desktop to consume. And so there's a lot of tooling that's been built around Mapbox vector tiles. And so that's not going to go away. And that's going to be a good use case for a lot of people for a long time. But the Arrow, at least for analytical data, is a good alternative. And it's the fuzzy line between what is visual and what is analytic data is.
But they might even, I mean, like, I think right now, BigQuery, Snowflake, DB, they all have already Arrow interfaces. This Arrow data AVA, Galak is a replacement to the ODBC or JDBC Galak contract with Arrow. So they are outputting already Arrow, and not GeoArrow.
Yeah, not GeoArrow.
That's obviously something that has to be kind of like in a way kind of work with them because they're working on GeoParquet. So those things are kind of connected. But like eventually you could see the data warehouse generating Arrow and pass it all the way down.
Yeah. You could have a as MVT and an as Arrow.
Or as a whole document, right? So it's document mode or tile mode in a way.
Yeah.
Can we go back to this? Or maybe we can just talk about it.
Oh, yeah?
Yeah, let's have like.
Well, people who want to eat can go eat.
Yeah, on your, you can go back to the slide that had the whole kind of pipeline from GeoPandas. It was red, I remember. That's the one.
There we go.
Like one example, you were just doing categorical filtering. And
Yes.
in general, like makes like that's why you're making the decisions that you're doing. But if you can look at it from the point of view of a user, then they have some kind of data set and they want to specify, say, some kind of column. And if they're working in Python, then they're maybe used to applying that column up there. If they're used to working, they might apply it on in the JavaScript level, or you might even apply it on the GPU. You can just like upload like a lookup texture and then just do it based on that. In a way, we end up in a situation where you can be implementing the same functionality in like 3 worlds in 3 different languages. And I think you know this yourself because you had to recreate a lot of stuff that we've already written in the Deck.gl world. So I just guess the question is like, do you have any thoughts on how we could like make it simpler to kind of port this kind of functionality between these parts? Like, is it the data format that makes it hard, or like, because it seems like there's a lot of duplication and that gives a lot of maintenance.
I mean, my own bet is that if the data format is stable in a binary and performant way, then it makes it easier to choose essentially here, do I prefer to apply the styling in Python and transfer the buffer, the output, or do I prefer to transfer a function that says, here's this color map, apply it in JavaScript? And so by making the data format efficient to exchange, then I can do wherever it's most convenient for the user. And for now, that convenience is in Python, not in JavaScript. But I don't know if that solves the problem of duplicating.
Because like for you then, so when you have like right? Then you're basically you're sending a range away from Python to the GPU. That's easy, but you don't want to have actual access to functions because you want to do the styling in Python.
Yeah.
So would it, for example, be better if Deck.gl had an API? I'm just like thinking out loud. If we kind of had like a color map and then just like a range that we could use to do this mapping, and then that way you could pass the range as you were before, and then some kind of color map, which would essentially be more binary data. Like, would the API kind of make it easier so we wouldn't have to do this thing again and again on?
Like maybe, but I feel like there's also probably some use cases where the user wants total control of their color map.
But that's fine, yeah. But like, because like I understand that I look at it from like, for me, the Deck.gl part is the one that's glowing and everything else is less important. But for a Python person, that's the glowing bit, and all of this is just like detail that I don't want to think about.
Yeah.
But so this is my viewpoint. But then when I kind of like see like all the calculation happening in the Python world and then 100 megs of memory being transferred across, I'm just like, why? Why don't you know the GPU would be so much faster? No. So I'm just trying to think of ways that it could be done more performantly.
Yeah, I mean, I think even if it is in theory more performant to send less data and do that calculation on the GPU or in JavaScript, that sometimes even when you're sending more data, as long as you have a fast enough connection or you're on the same machine, then it doesn't really matter if you're sending more data, because that enables the user to.
And you're sending like 10 million points or something, then it is just surely faster to have a column up that you've just sent through and then some kind of range that you're changing. Like, I haven't played around with it, but like you're not going to get 60 frames per second.
No, you're not going to. But like there, the thought is that you don't need 60 frames per second for changing a color map. Waiting like a second to swap a color map is fine. Or those are like the architectural decisions that I've chosen to make it ideally easy to maintain, and I don't want to maintain a function JavaScript function string.
Yeah.
It's one thought here, more than not a solution, but a thought. If you look at the Google BigQuery big data frames handle things, and like it looks a lot like a data frame object, and you are operating it in Python, but the computations happen somewhere else on the BigQuery
engine, stuff like that.
Yeah, but I think this one's notable from the perspective of you're still writing Python code that looks like it's operating on a data frame.
Yeah.
They've managed to inject a layer of indirection there that moves computation to a data warehouse. Yeah. I wonder if there's similar ways to look at a data frame differently that allows them to do computation around a little bit more portably there too.
I mean, there is this library called IBIS that tries to abstract tables, and so it's cool because it has a single the portable data frame library. It has a single API, and then it kind of has 20 backends where you can use DuckDB, Polars, Data Fusion, BigQuery, I assume, where this will translate into whatever backend it expects, so that you're working with a data frame, but that data frame could be local, and then you scale up to bigger data, and then it's remote. They also have some support for geospatial data, and they have an example with Lonboard, but still there, it is collecting the output of a query, downloading that output, and then passing that query into JavaScript. It's not something more native, like having tiles of a query